Okay, so this is section 13.3. This will be done in 2 days of lessons. So this is day one. We're talking about arc length and curvature. So arc length is something that we've talked about before. Curvature is not necessarily something that we have talked about. It's probably a word that you've either heard or some form of it, but maybe not something that we've talked about mathematically. All right, so we're going to be able to define and find arc length for three-dimensional curves and define the curvature of a function and what that means. So let's start off with back in 2 dimensions arc length. This is something that we have done before. So we'll do a real quick recap of what arc length is in 2 dimensions. So we're going to have some kind of a curve, whatever that curve is. Maybe it looks something like that. And in order to find the arc length, the concept was that if I take a bunch of points along this curve, maybe I'm trying to find the length of this curve from t equals 1 right there to t equals 2 out there. The idea was, if I can kind of estimate what each one of these little partitions is, and then use some kind of a method to be able to make those partitions really, really tiny, then I can actually figure out the length of the arc of the curve. So if I wanted to find the length between the first partition at T1 and maybe that second little green partition here, so between here and here, what I could do is I could take some kind of a change of x value, some kind of a change of y value, and then what that's going to do is allow me to form a right triangle, which is going to closely estimate, it won't be exactly the same, but it's going to allow me to closely estimate the arc length of the, or excuse me, that length of that arc in between those first 2 red dots. So the general concept here is as delta x, delta y both approach 0, or we're letting those changes become very, 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 very small, we call that, or call them, dx dt and dy dt, or derivative notation. So as your changes become really, really small, we start to let them become the derivative notation, dx dt, dy dt. So the arc length of this in particular curve, or any curve, would be integrating or taking all of those little partitions. And remember, what we're trying to say is that the distances between those 2 red dots are coming so infinitely small that the hypotenuse of each one of those triangles is basically exactly the same as the length of that part of the curve, because it's going to fit so closely. If we integrate from T1 to T2, or add up all of the lengths of the curve, well, remember that you basically using Pythagorean theorem to find the hypotenuse, it's going to be the square root of dx dt squared plus dy dt squared with respect to t, so dt. And that's how you would find the arc length in parametrics. Okay, so now we can extend that idea to 3-dimensional space. So now we've got a 3-dimensional grid, x, y, z. And we're going to go ahead and sketch some kind of a 3-dimensional curve floating up here in space. It's the same exact idea. We're just extending this now to 3 dimensions. So if I wanted to find the distance from here to here, well, it's going to have some kind of a change of x, staying parallel to the x-axis, some kind of a change in y, staying parallel to the y-axis, and then some kind of a change in z. So I've got a delta x, delta y, and a delta z. So the distance between the two green points is going to be the square root, and we've already developed this, the square root of delta x squared plus delta y squared plus delta z squared. It's just the change of the distances, all squared, added up, take the square root. So it should follow that if we let delta x, delta y, and delta z approach 0, they're going to become derivative notations in parametric form. So the arc length in 3 dimensions from some point to some other point, t1, t2, is the square root of dx dt squared plus dy dt squared plus dz dt squared with respect to t, so dt. And that's how we're going to find the arc length. So let's go ahead and look at example 1. Find the arc length of the helix, which is defined as cosine t, sine t, t, from 0 to 2 pi. So we want to find the arc length specifically from 0 to 2 pi. And while you don't necessarily have to draw this one, just to remind ourselves that this helix is going to start here, and then it's going to wind its way up around like this, come all the way back around, and then stop basically what would be over top of the original piece. So let's go ahead and draw our little arrows in there to show direction. And hopefully you can tell that there's some height there. Okay, so we can figure out the arc length. Our t values are going to go from 0 to 2 pi. It's going to be the square root of the derivative of x with respect to t is negative sine t. So negative sine t squared. The derivative of y with respect to t is cosine t squared. The derivative of t with respect to t is 1. So 1 squared dt. All right. So let's go ahead and simplify, because we don't want to try and take this without simplifying first. So this is going to give us, let's see, negative sine t squared is just going to be sine squared t plus cosine squared t plus 1. And the nice thing is, dt, and the nice thing is sine squared plus cosine squared is 1. So really what I'm taking the integral of is the square root of 1 plus 1, which is the square root of 2 dt. Square root of 2 is a constant, so antiderivative with respect to t is just going to be the square root of 2 times t from 0 to 2 pi, which is going to be 2 pi square root of 2 minus 0. So it's 2 pi square root of 2 units, whatever the units would be. And that's it. That's the idea behind arc length. Okay, let's look at another example. Find the arc length if r of t is I plus t squared j plus t cubed k from 0 to 1. So in this case, it might help. It's just personal preference if you wrote this in our vector notation like this. So it looks like it's 1 t squared t cubed. Sometimes it's just easier to see it from that form. All right, so we need to find the arc length from 0 to 1. dx dt, well, that's 0. Derivative of 1 is 0. So 0 squared. dy dt is going to be 2t, so we'll have 2t squared. dz dt is 3t squared, so 3t squared squared dt. Okay, let's simplify. So we're going to get 4t squared plus 9t to the fourth. 9t to the fourth plus 4t squared. Okay, it looks like I can factor a t out. So it looks like we're going to get t squared 9t squared plus 4 dt. I can split that t squared times 9t squared plus 4 under the square root. Taking the square root of the t squared out to the front just gives me a t on the outside. Still leaving 9t squared plus 4 on the inside. But that's important because now I can actually use a u substitution here to be able to solve this integral. So up here, u is going to be 9t squared plus 4. Du is going to be 18t dt. So dt is going to be du over 18t. All right, so let's see here. Now we're going to get the integral of t times the square root of u times du over 18t. I'm going to go ahead and I think change the bounds here. So plugging 0 in to this right here to get my new u value is going to give me 4. Plugging 1 into that is going to give me 13. So now I don't have to worry about changing this back at the end. The t's are going to divide away. It's kind of what we needed to do there. We can pull the 1/18 out to the front. And then I'm going to have left over u to the 1/2 du, which I can take the antiderivative of. So we're going to get 1/18. So u to the 1/2 antiderivative is going to be u to the 3/2 divided by 3/2, which is multiplying by 2/3 from 4 to 13. So let's see, that's going to be 1 over 27. 1 over 27. And then 13 to the 3/2 minus 4 to the 3/2. Not a pretty answer, but that is the arc length. Okay, you might see it written in a different way because you can actually make 4 to the 3/2 8. Take the square root of 4, it's 2, cube it, it's 8. 13 doesn't work out very nicely, so you'll probably just leave it like that. All right, normally I would do a slightly longer video, but we're going to start reparameterization next, so we'll come back with a second video for that part.